This lecture is on Lewis dot structures and continuing talking more about bonding. So the purpose of this lecture is to have you guys be able to draw valid Lewis dot structures for molecules that obey the octet rule. All right, so some things we need to, I guess, review before we talk about Lewis structures. So there's a huge difference between ionic and covalent bonds. And the main thing that you should remember is that in ionic bonds, electrons are transferred. And these occur between a metal and a non-metal. In a covalent bond, electrons are shared. And these type of bonds occur between a nonmetal and a different nonmetal, or even the same nonmetal, but two or more nonmetals. All right, number 2, how does an atom's electron configuration relate to the octet rule in ionic compounds, and then in covalent compounds? So in ionic compounds, remember elements will either gain electrons or lose electrons in order to have an electron configuration of a noble gas. And in covalent compounds, the goal is for both elements to have an octet of electrons, to have those eight electrons that makes it have stability, not really, but make it look like it has the stability of a noble gas. So what is the definition of electronegativity, and what is the trend in the periodic table? So electronegativity, remember, is the affinity of an atom to be able to attract electrons to itself in a bond. The way that I told my students, which is not really the book way, but it's true, it's basically how badly an element wants electrons. And some elements want electrons way more than other elements. And what's the trend in the periodic table? So just remember that electronegativity increases as you move across a period, and it increases as you move up on the table. However, we exclude the noble gases because they don't have electronegativities. They don't want electrons at all. They're already really stable, and they don't need them. So the halogens, fluorine is the most electronegative element on the table. Okay, so again, just the fundamental difference between ionic and molecular compounds. Ionic involves a transfer of electrons, and the bond itself, there's like nothing actually connecting the two ions together. It's just the fact that one is positive and one is negative, and they're attracted to each other. In molecular or covalent compounds, remember those words are used interchangeably. Electrons are shared, and that's what the bond is formed by. So you'll notice that here they've circled 2 electrons. So those 2 valence electrons will form a bond between these 2 nonmetals. All right, so remember valence electrons are in the main group. In the main group elements are shown by how many electrons are in the S and P part of like the configuration. So if we take a look here at group 1, and I'm going to really quickly pull up a periodic table. So group 1 is this guy. So anything in this column has 1 valence electron. Anything in group 2 has 2 valence electrons. Remember, we skip over the D block. Anything in group 13 has 3 valence, 4 valence, 5, 6, 7, and 8 valence electrons for those noble gases, with the exception of helium, which only has 2 valence electrons. All of the other noble gases have 8. So these numbers can kind of like help you remember how many valence electrons each element has. And once you get over to the P block, just take away the 1, and again, this will just show you how many valence electrons. And then again, helium has an exception, it only has 2. Okay, so that's exactly what this slide is showing us. All of the elements in group 1 have a configuration that ends in S1. All of the elements in group 2 have a configuration that ends in S2. That's where those 2 valence electrons come from. In group 13, all of the elements end in S2, P1. The total there is 3, right? S2, P2, total there is 4, and so on. So you can see how we get that valence number of electrons. All right, so when we draw our dot structures, remember we use a dot to represent valence electrons. So here's for, I guess, the first 3 periods in the periodic table, so like the first 3 rows going all the way across. Remember, 1 valence electron, we don't like pair up electrons. We put them on opposite sides, or it doesn't matter if they're on opposite sides, but we just keep them separated. Here we have 3, 4, one valence electron on each side, and then once they run out, like you run out of sides, you start pairing them up. So there's 4, here's 5, here's 6, 7, and then 8 for the noble gases, with the exception of helium. Remember, helium is a noble gas, so it is stable, but here we actually do draw the dots on the same side, just to show that helium doesn't necessarily want 8 electrons. It's happy with 2 because that fills its shell. So just make a note here, and it's in pink so you can remember it. Hydrogen and helium complete a duet. All the other elements are looking for an octet except for hydrogen and helium. These guys are actually happy with 2 electrons. All right, and as a reminder at the bottom, valence electrons are the electrons that make bonds, which is what we're going to look at here. All right, so ionic compounds. Remember, this is a transfer of electrons to produce ions with an octet. And again, an octet just means 8, so we're looking for 8 valence electrons like a noble gas. All right, so what we're going to do is draw the valence electrons first. So I'm going to go over to sodium. All right, sodium is in group 1, so here's 1 valence electron. And chlorine is in group 17, so that means 7 valence electrons. So there's 1, 2, 3, 4. Now we can pair up 5, 6, 7. All right, so this is what they look like, but remember, we're looking for an electron transfer. So it looks like chlorine here only needs 1 more electron to look like a noble gas. It already has 7 valence electrons. It's only 1 electron away from an octet. Sodium, if I take a look at where it is on the periodic table, all right, has 1 valence electron. If I lose that valence electron, then it can actually look like neon in its electron configuration. Okay, so I am going to go back to the presentation, all right, and have sodium give up its electron and give it to chlorine. As a result, sodium has lost something negative, which makes it a positive 1. And chlorine gained an electron, so now I'm just going to rewrite Cl, and this time I'm actually going to draw it with 8 valence electrons. Remember, it gained 1 electron. By gaining something negative, it has formed a negative 1 charge. So this is actually what the what's going to be formed as a result of this ionic bond. All right, so the name of this, okay, we can see that we have obviously a metal and a non-metal, so we're just going to name the first element, which is sodium, and then we're going to change the ending of chlorine to chloride. All right, now the next compound. So we have barium and chlorine. So we're going to go ahead and draw our valence dots. So barium, just want to, oops, thought that was going to swipe out. Just want to double check where that is on the periodic table. All right, we can see that it has 2 valence electrons. And then chlorine, okay, so again, here has 7. barium. Here's 2 valence electrons. All right, and then chlorine. Here's 1, 2, 3, 4, 5, 6, 7. All right, well, I can see that barium can donate one of those electrons to chlorine, but it still has another valence electron. Okay, so it still has this guy. So what we can do is actually add another chlorine that will accept that electron. So now we have somewhere else to put it. All right, and what we actually end up with then, since barium lost 2 electrons, it forms a positive 2 charge, and then we end up with chlorine having an octet, -1, and another chlorine with an octet, -1. All right, so then the name of this compound is barium chloride. All right, so remember, this is similar to what we had learned when we were formula writing. Like if you use your ion sheet, you can see that sodium is Na+1, chlorine is Cl-1. So to put them together, that's already a neutral compound, NaCl. When you look at barium and chloride, so barium is a +2 charge, chloride is a -1. So again, we can crisscross those numbers, BaCl2. So this is just representing the fact that we're going to need 2 chlorines to balance out that +2 charge on the barium. All right, so it says to draw Lewis dot structures for aluminum and oxygen, and then let's show the electrons transferring from one element to the other. Finally, name the compound. Okay, so we have aluminum and oxygen. So really quick, I'm just going to pull up the table. We can draw our valence electrons. All right, so aluminum here gets 3 valence electrons, and then oxygen, that one gets 6 valence electrons. All right, so let's go back. Aluminum, oopsie, wrong pen. All right, 1, 2, 3. Oxygen gets 1, 2, 3, 4. And I know I'm going to be combining it with aluminum in the bond, or like having electrons donated to it from aluminum. So I know this needs 6 valence electrons. Usually I tend to pair up the ones that are furthest away from the element, the other element, I guess. That way I have somewhere to like donate the electrons to. It just makes it easier to draw, basically. Okay, so what we have here is I can donate maybe this electron to that pair, and it will give another electron to oxygen. I can do the same thing here and have oxygen gain another electron. So again, oxygen has an octet. However, aluminum still has an extra electron. So we're going to draw another oxygen. Same deal with 6 valence electrons. 3, 4, 5, 6. All right, now aluminum can give up this electron to the new oxygen. Okay, well, now oxygen still doesn't have an octet, so we can go ahead and add another aluminum. 3 valence electrons. All right, so, okay, well, here's the electron can go there. But again, I still have that aluminum with 2 valence electrons with nowhere to go. So I'll add on another oxygen. So you basically keep going until it's a complete transfer of electrons. All right, so there's 6. Oh, look, now it's like going to be perfect. We'll have this guy go here and this guy go here. All right, so what we'll have formed as a result of this is aluminum, 3 electrons donated for each aluminum, so that means a +3 charge. All right, and then I'll have oxygen, 3 oxygens with complete octets, so I'm going to draw 8 electrons. All right, and since normally oxygen has 6 valence electrons, they've gained 2 each. Their charge is -2. Okay, so I can do the same thing for every oxygen that we had here, because each oxygen accepted 2 extra electrons. right, and then just a reminder, if you look at your ion sheet, aluminum is +3, oxygen is -2. We can crisscross our numbers and see that our formula is Al2O3, which totally works with what we just drew. We had 2 aluminums and 3 oxygen ions. All right, so then name the compound, aluminum oxide. All right, so in covalent compounds, something else happens. So remember, we are not transferring electrons. So I'm not going to see any pictures like this with me like drawing arrows and making things that have charges. So I'm not going to be making these ions anymore. In covalent compounds, we're going to share electrons. So again, the goal is for each atom to complete their octet by sharing electrons. And the shared electrons between atoms, so again, a pair of electrons, these guys are a pair of electrons, is a bond represented by a line. So like instead of, here we have H2O. Okay, so we have oxygen, and I'm going to draw it like this with the 6 valence electrons. All right, and then hydrogen here and a hydrogen here, because it says I'm going to have 2 hydrogens. All right, and here's a dot. Here's 1 valence electron each per hydrogen. So instead of leaving it like this, I could make a bond between the 2, 2 hydrogens to the side. I'm not going to leave it like that, though. So instead, what we do is we just draw a line. But it's known that every single time that we draw a line, that means 2 electrons. Okay, 2 electrons. So then if I go back and I count around the oxygen atom, I'm going to use a different color so we can see it better. Let's go with this, actually. All right, so here I have 1, 2, 3, 4, 5, 6. Remember, that counts as 2 electrons, 7, 8. So there are 8 electrons now around oxygen. All right, I'm going to backtrack and then redraw that just so we can see. We've got 1, 2, 3, 4, 5, 6, 7, 8 electrons around oxygen. Hydrogen, so this hydrogen only has that bond, which is 2 electrons. And this hydrogen also only has that bond, which is 2 electrons. Remember, that's okay. Hydrogen and helium, remember, are okay with a duet or only 2 electrons. All right, so again, there are some exceptions to the octet rule, and we've already mentioned the first one. Hydrogen and helium are okay with a duet, so they do not want more than those 2 electrons. They can't hold them. So if you think about their configurations, both of these guys are 1s, hydrogen's 1s1, and helium is 1s2. The 1s orbital only has 2 electrons. It can only hold 2 electrons. And since they only exist, I guess, as 1s2 as the maximum for helium, it doesn't have those other orbitals. It only has the ones that it can fill. So that's why those 2 elements are happy with the duet. The other exception is that boron and beryllium can form incomplete octets. So if I take a look at the compound the way it's drawn right here, so here's boron, I can see I've got 3 bonds. Remember, each bond is actually 2 electrons. So this is 1, 2, 3, 4, 5, 6. So it actually only has 6 electrons versus like the ideal, which again would be 8. That's okay though, because boron and beryllium can form incomplete octets. So the way that I remember these 4 elements, hydrogen, helium, boron, beryllium. So 1, it kind of rhymes. And 2, if you can remember H and B, just add E's to both of those. So He, Be. But you can remember them this way too. All right, and then there is such a thing as expanded octets, and we'll talk about that soon. Expanded octets are possible with D shell electrons. So the idea is that if you have an element in the third period or later, remember, period 3 is where the D block comes in, right? Like you're in 4s, and then the next part of your configuration would be 3D. That's a whole slew of more orbitals. So normally, elements would want an octet, and like that's the max. However, once you get to period 3 and you have all those extra orbitals there, it is possible for elements to have more than an octet. But again, we'll talk about that later. All right, so some steps when you're drawing a Lewis structure. You're going to count valence electrons, so you're going to add up the total from the compound. You're going to draw the skeletal structure. So basically, this just means like the simplest form or the simplest structure you can draw to connect the atoms to each other. In number 3, you're going to connect the atoms to the central atom with single bonds. Then you're going to distribute electrons. And then it says here that you're going to do terminal atoms first. So all that means is you're going to fill in the valence electrons or distribute these electrons onto the end atoms, not the central atom. So you're going to do it on the central or on the end atoms. And then if there's, I guess, nowhere else to put them, then you start putting the electrons on the central atom. After you're done, you're going to double check to make sure that you have completed the octet around the central atom. And if you haven't, you're going to form double or triple bonds, but only if you need to. Only if you don't have enough valence electrons on that central atom, and if it's not one of our exceptions that we talked about. So H, E, B, E. Remember, these guys are duets. They're happy with 2 electrons, and these 2 elements can have less than an octet and be fine. All right, so some other notes. Hydrogen atoms can only form single bonds, so they're always at the ends, and oftentimes they're bonded to carbon, nitrogen, and oxygen. But again, for our purposes, these guys are always going to be at the ends. You're never going to see a central hydrogen. Why? Remember, they are happy with 2 electrons, so a duet. So they're happy with a single bond to them and done. Oxygen tends to have 2 bonds, nitrogen usually has 3, and then carbon has 4. Most of the time, but this can change. All right, if we're looking at ions, so let's say that like my regular, okay, let's pretend here. So my regular compound is CH4. So to get the total number of valence here, what I would do is like, okay, well, carbon has 4 valence, hydrogen has 1 valence, but I've got 4 of them according to the formula. So if I take that, I'm going to get a total of 8 valence electrons. Okay, so when I'm counting up to draw my molecule, that's what I would start with, 8 valence electrons. Now, this is saying if we have ions. So let's pretend that I have something like NO3 minus 1. So here, my nitrogen has 5 valence electrons. And you might be asking, like, where is she getting those numbers? Remember, this is like from what column they're in the periodic table. I know that nitrogen's column has 5 valence electrons. And there's only 1 nitrogen, so the total from nitrogen is 5. Oxygen, which is the next element there, has 6 valence electrons. But according to this formula, I've got 3 of them. So the total, I guess, contribution from oxygen to valence electrons is going to be 18. All right, and then the last step is this. I do have a negative charge. All right, so instead of just saying, 18 plus 5, 23. That's 23 electrons. But I have a negative charge. This negative charge means that I'm adding 1 more electron. And it's saying 1 because it's -1. If it had a charge of -2, then I would be adding 2 electrons. So my total number here would be 24 electrons. So negative charges get added because we're adding electrons. And if I had a positive charge, I would actually take away an electron. Remember, that's actually what makes that ion positive, because it donated an electron. All right? And so we're going to use the electronegativity table to figure out what atom goes in the center. The least electronegative atom goes in the center. The other thing I like to tell students, if you don't know which atom is going to be in the middle, chemistry likes symmetry. So if you can make a molecule symmetrical, do it. And that's probably what it looks like. Oh my gosh, I don't know how to spell symmetry. Symmetry. Looks like too many M's, but I think so. So try to make molecules symmetrical, and chances are it probably looks like that. All right, so here's that electronegativity chart. If you are stuck and you don't know like how to make something symmetrical, use this chart to figure out which element would go in to be the central atom. And as a refresher, so we're saying here the least electronegative atom goes in the center. So in this direction. Okay, so this would be decreasing electronegativity. Or you could just look at these values. So whichever one would have the lower electronegativity, that's probably going to be the central atom. Except never, never, never hydrogen. All right, so we're going to draw the electron dot formula for PCl3. So the first thing we need to do is count our total number of valence electrons. All right, so I should do that up here. So phosphorus and then chlorine. So phosphorus, I'm going to take a look at where it is in the periodic table. All right, it's right here. So phosphorus has 5 valence electrons that it's going to bring to the diagram, or the valence electron total. All right, and I only have 1 phosphorus, so times 1, 5 electrons from that. Okay, so then we can look at chlorine. If I go to chlorine, here's chlorine. It has 7 valence electrons. So now I can go back and say that I need 7 valence electrons for each chlorine. But according to the formula, I actually have 3 of them. So times 3. All right, now I can 21 electrons. I'm going to add these guys up. All right, get a total of 26 valence electrons. All right, then we're going to draw the skeletal structure. So basically, this is where we're looking at like making it symmetrical. There's 1 P and there's 3 chlorines. So it looks like the phosphorus will be in the center with the 3 chlorines just like kind of surrounding it. All right, so next we are going to connect atoms to the central atom with single bonds. All right, so remember our total number of electrons here was 26 valence electrons. So when I start connecting these guys with bonds, we're taking some of those away. Remember, each bond is 2 electrons. So this is like 1, 2, 3, 4, 5. I'm only labeling them to like help you keep track of how many we have used already. 5, 6. So we've used 6 valence electrons. All right, then it says that we're going to place the remaining electrons at terminal atoms. So remember, this just means end atoms, not the central atom. And then we're going to use single or multiple bonds to complete octets. So I'm going to actually go back up here so I can steal this picture and paste it down below so we can, oh no, why'd I delete it? So we can continue drawing on it. Copy. Paste. Okay. So here's our guy. So right now I've only used 6 valence electrons. Remember, the total that I had was 26. All right, so 5, 6. Now I can start drawing my electrons on terminal atoms. So this is 7, oopsie, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then I've run out of space, 25, 26. So then I put them on the central atom at the end. so now we can do the same thing for a different formula. So we have ClO3. Okay, so this is what I'd like to do. I'm going to count up my total. ClO, chlorine has 7 valence electrons. There's only 1 chlorine here, so that's 7. All right, oxygen has 6 valence electrons, but I have 3 oxygens, so that means a total of 18 electrons. All right, so the total here so far is 25 electrons. But don't forget, we need to account for the fact that this thing has a negative charge. If it's negative, remember, I'm going to add another electron. So I have a total of 26 electrons. You're always going to have an even number. If you don't have an even number, that means you probably didn't consider the charge. All right, so here's our even number, 26 electrons, and I can go ahead and, remember, draw my skeletal structure. If I take a look at what this looks like, I've got 3 oxygens, but 1 chlorine. Chlorine's going to be my central atom. Again, chemistry like symmetry. So here's Cl. I'll draw my 3 oxygens kind of hanging around, and then we'll start counting to 26. Remember, each bond that I draw is 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and then I've run out of room, 25, 26. Since this one was an ion, had a negative charge, we put those in brackets, and then we put the charge on the outside. Only for ions, though. Oh, let's go back really quick. I just want to show you how every element's octet has been fulfilled. Okay, so I'll use yellow for the oxygens. 1, 2, 3, 4, 5, 6, 7, 8. Remember, each bond is worth 2. And that goes the same way for every other oxygen on this molecule. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Octets fulfilled. Let's take a look at chlorine. So I'll use orange for that. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so all of these elements have their octets fulfilled. All right, if there are not enough valence electrons to complete octets, that's when you know we're going to need multiple bonds. In a single bond, 1 pair of electrons is shared. In a double bond, 2 pairs of electrons are shared, and then in a triple bond, 3 pairs of electrons are shared. All right, so let's take a look at when that would happen. All right, so carbon dioxide is CO2. So let's kind of follow the regular steps and then see why we need those multiple bonds. So here's carbon, here's oxygen. Carbon has a total of 4 valence electrons, and there's only 1 carbon in this molecule. All right, oxygen has 6 valence electrons, and there's 2 in this molecule. So it's 12. All right, so my total here is 16 electrons. So now I'm going to sketch my molecule, CO2. So 2 oxygens, 1 carbon. We'll put the carbon in the middle. Here's an oxygen, here's an oxygen. All right, well, if I draw my bonds to connect these guys, remember I need to get up to 16. That's my total. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so I've drawn all of my electrons, but oxygen has satisfied octets. So if I go back and count, 1, 2, 3, 4, 5, 6, 7, 8. Same thing for oxygen here, 1, 2, 3, 4, 5, 6, 7, 8. But carbon only has 4 because of the 2 bonds, 1, 2, 3, 4. So because that happens, we know that carbon does not have a satisfied octet. So what we're actually going to do is erase one of the lone pairs. So I'm going to cross out this lone pair and say, okay, well, let's share those 2 electrons instead. So I'm going to redraw this with a double bond to carbon and this oxygen with only 2 lone pairs on it. All right, and if I do that, okay, oh, I drew an extra guy. If I do that, I can see that, okay, well, this oxygen on the left-hand side still has a satisfied octet. 1, 2, 3, 4, 5, 6, 7, 8. So remember, we're sharing electrons. So this oxygen is okay, but carbon still does not have an octet. Right now, carbon only has 6 valence electrons. So we're going to do the same thing from the other side. Again, symmetry if you can. So we are going to, I'm not going to redraw it, but I'll just erase the lone pair all the way on the right-hand side. So I'm taking it off. And instead, I'll have oxygen share those electrons so that carbon can now have an octet. All right, so if I go and count, okay, carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it's sharing with those oxygens, all right, which is perfect. So this is our formula for carbon dioxide. Right, nitrogen actually has a triple bond. So nitrogen has, nitrogen has a total of 5 valence electrons. And so we need a total of 10 because we've got 2 nitrogens. Right, if I were to draw those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so if you still need help on drawing Lewis dot structures, go ahead and maybe watch this video, this linked video, but we can do a few more practice problems. Okay, so the first one here, CCl4. So carbon, tetrachloride. All right, well, carbon has a total of 4 valence electrons on the periodic table, and chlorine has a total of 7, but we have 4 chlorines. So that's 28 plus 4, that's a total of 32 electrons. All right, let's draw our skeletal structure first. 1 carbon, that must be the central atom, and I have 4 chlorines. So I'll just kind of spread them out around this carbon. Okay, I'm going to connect the single bonds first and then start drawing lone pairs on the terminal or outside atoms. So I need to get to 32 total. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so it looks like chlorine's octet is fulfilled. 1, 2, 3, 4, 5, 6, 7, 8. And then all of these chlorines look the same, so they have fulfilled octets. Now I'm just going to go back and make sure carbon has a fulfilled octet. 1, 2, 3, 4, 5, 6, 7, 8. It's good. So this is our final structure for that. All right, the next problem tells us that we're going to draw C2H2. And then they tell us that this is our skeleton. Basically, it's telling you, like, hey, this is the way that they're organized. So first thing I'm going to do, though, is add up my electrons. Carbon has 4, but I've got 2 carbons, so that's a total of 8. Hydrogen has 2. Or there's 2 hydrogens, sorry, but there's 1 valence electron each, so 2 from the. So our total here is 10 valence electrons. All right, so carbon, carbon, hydrogen, hydrogen. So I need to get to a total of 10. but I need to count the bonds that we've already been given. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, notice how I did not draw, this time I didn't draw those lone pairs on hydrogen. Remember, hydrogen's happy with the duet, which both of these guys already have. Remember, a bond is 2 electrons. So I had to draw them on the carbons. But now we need to rearrange them, because if I start counting, they don't have an octet. 1, 2, 3, 4, 5, 6. And the other carbon looks exactly the same way. It only has 6 valence electrons. Remember what we can do? We can take a lone pair off of an atom and share them. So I'm actually going to erase this lone pair above the carbon here. Okay, maybe not. And have it share those electrons instead. All right, so this carbon still only has 6 valence electrons. 1, 2, 3, 4, 5, 6. So we can do then is remove the other lone pair on the other carbon and also redraw that as a bond. All right, so then I have 1, 2, 3, 4, 5, 6, 7, 8. Now each of the carbons has an octet. The hydrogens have duets, so we're done with that structure. All right. Hopefully this helped, and drawing Lewis structures won't be too bad.